Hi, this video covers what I've learned over the past 2 months working with the new Rohde and Schwarz MXO4 oscilloscope. And yes, after a long online debate, that is how one is supposed to pronounce a manufacturer name.
Rohde und Schwarz.
After the first 2 months of use, I have to say that the functionality and usability of the instrument doesn't disappoint. I truly hope that what they've done in the MXO4 should trickle down into other R&S instruments so that many engineers can benefit from the features. In this review, I'll try to show what the MXO4 does as best as I can so that you too can decide for yourself how it performs. I should also mention that there is a longer written review as well that covers things in more detail. Also, if you wish to ask any questions or have comments, then please do so, and then myself or others can help out as best as possible. There is also a whole series of blogs on the MXO4 which Michael Kellett has written, so all in all there are several resources to use to get as much insight as possible, since one doesn't upgrade oscilloscopes every day and you'll want to know as much as possible in your area of interest. The MXO4 is intended for hardware and firmware design engineers working in all sorts of industries. The low noise and 12-bit resolution should make the instrument useful for noise measurements, examining power supplies, and also power measurements, for instance when working with FPGAs and microcontrollers or sensor-based hardware as well. There is a dual 16-bit waveform generation capability, which is useful if you need controlled stimulus, for instance for frequency response work, and for testing filters and other signal conditioning circuits, or for working with DSPs, or for applying high-power signals to RF mixers, or for IQ signal generation. The spectral analysis is intended for seeing signals with more insight and detail than would be possible with a time domain view. So this should suit things such as examining filters and oscillators and for minimizing distortion in systems, but also particularly if you're developing new hardware and wish to test for electromagnetic compatibility during the development process. If you're developing firmware, then the MXO4 should be usable for examining data buses, working with memory devices, and also onboard high-speed or off-board industrial protocols, even when there are large data streams containing thousands of bytes being transferred, since the instrument has a lot of sample memory. But usability will also be important, so that will be examined in the review as well. Also, it is key to see if any remote control or programmability features are usable so that the instrument can be inserted into larger test solutions, or for performing more complicated test sequences, or for more deeper analysis with post-processing. The MXO supports data export in Python format, so that will be investigated as well. These are the kinds of features that can help future-proof instruments so that they can continue to be useful as designs and test needs change. The unit has all expected connectivity, especially lots of USB ports for mouse, keyboard, etc., and HDMI for simultaneous display. The touch is responsive, and the buttons and rotary controls feel fine too, and they can be pushed into reset positions of cursors and so on. The fan is very quiet and unnoticeable during instrument use. The supplied scope probes have stiffer cable compared to Tektronix's probe cable, so that's a negative, but on the plus side the probes are a bit smaller and the tips are finer and sharper as well. There's a ton of accessories in an optionally purchasable pack, but the tips fit 2.5mm audio jacks, so homemade adapters are a possibility. But please don't blame me if you copy this and snap the probe tips because they do look quite delicate. The logic probes look great. They're in 2 sets of 8 with super flexible cables that plug into the Spider adapter pod. There are lots of accessories like grippers and pin header sockets that are supplied with the logic probe set. There are lots of ways to use a scope. If it's not within arm's reach, then a web browser could be used. It could be a tablet, or you could plug in a USB mouse or trackpad, and that could be wireless. Since the resolution is so high, new ways are needed to visualize the data, and one of them is the zoom capability. You can just drag to select an area, or there is a menu where the X and Y positions of the area of interest can be selected and adjusted for really precise zoom. For this example, I used a fast edge square wave generator. It's very easy to build and very low cost, and it outputs selectable 0.1 or 1 or 10 MHz. The MXO4 solves a problem that other scopes have, which is that in single trace capture mode, the trace has a thin line with noise on it, so by instinct people just use the run stop button instead to get the benefits of the persistence view. With ultra high-res scopes with zoom capability, the single capture becomes very unacceptable because there's no idea if there's noise on the signal or not, without the benefit of persistence. By changing a value called n single, it defines how many acquisitions are done when the single button is pressed. Now there's no problem seeing the waveform trend. Even better, if a glitch is caught, then it can be replayed because every single acquisition that made up the display can be individually observed using a control called history. It's a very elegant solution. I love it. On the subject of viewing close-up detail, it is worth mentioning that good spectral analysis is essential for high-res scopes because they will reveal the detail that is impossible to see from the time domain view. Fortunately, the MXO4 has stunning spectrum analyzer capability, which will be discussed shortly. I wanted to use the MXO for measuring ferrite and inductor performance, so I built up a testbed that consists of a MOSFET switching power through an inductor. It's controlled by PWM set to a very brief pulse width using the MXO's waveform generator. The current is measured using a sense resistor, and just to see if it worked, I used a very low 10 milliohm resistance for that. I used the mass capabilities in the instrument to essentially provide the measured inductance with the mass channel M5, which will be the blue trace. The y-axis shows the inductance in microhenries. The initial green hump is nothing to do with the inductor. It is a limitation with the testbed because the MOSFET gate drive gets coupled into the sense signal. It doesn't matter because it doesn't affect the measurement after a couple of hundred nanoseconds. I could easily see the value when the inductor was unsaturated and the decline as it became saturated. The capabilities were good for this scenario, but it would be better if more mass terms could be chained up. I think the current 5 terms is not enough. 10 would be better. There have been some recent improvements in these capabilities in the latest firmware release, so I will retest. Anyway, back to the task at hand. I liked that things ran fast enough and in enough detail that real-time measurements of the inductor were possible down to fractions of a microhenry. This would be great for tweaking the inductor, changing its temperature and so on, and immediately seeing the effect. Also, the built-in waveform generator was more than capable at providing very fine pulse widths, so there was little risk of damaging the MOSFET when the inductor becomes saturated. Another use case for the instrument is to measure current or power consumption. I didn't have a current probe, but the high sensitivity of the instrument means that a low-value sense resistor could be used. 2 coax connections could be made to the circuit, one for measuring the voltage and the other for the voltage across the sense resistor, since the scope input channel can be configured with the resistance value, which is volts per amp basically, to directly show the current consumption. I made up this board for testing USB-powered devices. The twisted pair current sensor wires were threaded into insulation taken from PTFE insulated wire and then covered in braid soaked in solder for shielding. This worked okay, but it would be better to redesign this, perhaps putting traces behind copper planes on a multi-layer PCB. I used a 25 milliohm resistor, which is very low for the current that I was expecting. I did this mainly just to see how the MXO would handle the small signal. I was especially keen to try this with an FPGA board because it could be extremely handy for monitoring if outputs were incorrectly driving things or even for troubleshooting by retasking a status LED. For this test, the FPGA was configured to drive a VGA monitor as an example task just to consume power, and then also simultaneously toggle an LED with 5 milliamps of load to see if that small additional load current could be detected. And the total current was about 100 milliamps at 5 volts. The 5 milliamps from the LED was resolvable as shown in the yellow current measurement. The MXO here is showing current at a resolution of 40 milliamps per division, which seems quite nice for embedded systems work. The blue trace shows a power calculation, which is about 500 milliwatts as expected. The scale is 200 milliwatts per division. In summary, the sense resistor approach, even with a very low 25 milliohm resistance, is more than good enough to resolve milliamp level differences on a device consuming hundreds of milliwatts of power. The spectral analysis is very essential for modern scopes, and especially high resolution ones, because it's impossible to make maximum use of the high resolution from time domain views. The spectrum view is used to pull out signals that can't be seen in the time domain signal representation, regardless of how much the signal is zoomed in. To check out the capabilities, I connected the MXO to an untested low-noise power supply design. In hindsight, a coax cable and DC blocking capacitor might have been a better way to connect it, but I used a scope probe for this test. The controls on the spectrum view are very similar to those on a normal spectrum analyzer instrument, they are broadly decoupled from the time domain view. The resolution bandwidth can be set to very low values, and the display still updates fast like a real-time spectral analyzer or a software-defined radio. A major benefit, though, is that it works down to DC. Here the instrument is set for a 40 MHz span. The automatic peak markers are brilliant and it updates fast. The noise floor in this test was about 10 microvolts RMS, and the signals poking out from above the noise floor were higher than I hoped for from this power supply. It turned out to be an issue with the AC to DC mains adapter. After replacing that with a better one and adding a ferrite core, I could easily see the improvement. Here's the view from DC to 1 MHz. In the past, I'd have needed to use a preamplifier to see this level of detail. Unfortunately, there is no logarithmic frequency scale capability, but I have suggested that as a feature request in case Rohde and Schwarz are interested. I'm looking forward to using the MXO with RF circuits, and as a first test I connected it up to the 10.7 MHz intermediate frequency output taken from an FM radio. The results were impressive. The span here is set to 500 kHz. The fast responding display is comparable to software-defined radio displays, but many SDRs won't work at such low frequencies.
बदकिस्मती से सभी ऑर्गेनाइजेशंस के लिए साइबर क्राइम एक बड़ा खतरा बन गया है। पिछले बरस 39% यूके बिजनेसेस पर साइबर अटैक हुआ और छोटे बिजनेसेस को तकरीबन 3000 पाउंड तक का नुकसान हुआ। नेशनल साइबर सिक्योरिटी का कहना है कि अगर आपके पास
The resolution bandwidth here is 100 Hz, but there doesn't seem to be any real practical limit. It's possible to have resolution bandwidths well under 1 Hz with the MXO. That's a higher resolution than any spectrum analyzer I've ever used. There's no waterfall display, unfortunately. That would have been the icing on the cake, but it is possible to enable a color palette to see some of the dynamic characteristics of the spectrum.
Search Cyber Action Plan now or visit ncsc.gov.uk/cyber-aware/action plan.
The best mix of music. Asian Star Radio.
Another neat use case for the spectrum analyzer functionality is to perform EMC testing to see what unwanted content is emanating from the equipment under test. The type of testing I'm thinking of is that which could be performed more frequently than pre-compliance tests, and of course at a far lower cost than formal testing in a lab. In other words, I was curious if EMC testing on the fly could be performed during product development. I have the 500 MHz MXO model, and there could be emissions at higher frequencies, but often those are a result of harmonics from lower frequencies like clocks, etc. So there is still value in testing, even if 500 MHz is the limit. Obviously, this doesn't help with things like spurious content at higher frequencies, but that can be identified in later pre-compliance testing with alternative test equipment. I think if the MXO could be used, then the benefit is that more frequent EMC testing could be done during development. For conducted emissions testing, I wanted to use the maths capabilities to separate out the common mode and the differential mode noise. The diagram here shows a general idea. A couple of line impedance stabilization networks are needed to isolate the DC power supply, and then the noise present on the power rails is coupled into two channels on the scope. The MXO is configured to show the spectrum of either the sum or the difference of the channels, which represents the common mode or the differential mode noise respectively. This minimal circuit is part of standards and is easy to construct, although it is better to add some protection against transient voltages. The circuit I used is a very basic minimal circuit, since this was an initial proof of concept. However, now that it works, I do plan on building a better one on a proper circuit board. It is quite easy to make. The inductors were 0.7mm enamelled wire with 20 turns on an 8mm drill bit. The circuit was taped inside a biscuit tin, which I use for temporarily shielding circuits. The tin has hole drills with a couple of SMA connectors fitted for quickly placing a circuit inside. The device under test was a Raspberry Pi 3B connected to a 7-inch TFT screen. There are diagrams in standards documents to show how everything needs to be placed, and a metal ground plane is a must, but I tried a very cut-down option for now, which was to use the power supply chassis as the ground plane. The biscuit tin was placed on top of that, and then the Pi with display was placed on top of that as well to kind of make a grounded tower. This is obviously not recommended, so the results will not be representative of what a real setup would achieve. The spectrum display with the power off was recorded as a reference spectrum capture, and then the power was switched on. The MXO4 allows for the spectrum to be displayed from a maths channel, so the display here is set to be the sum of C1 plus C2, which should reveal the common mode noise. That noise could come from high-frequency clocks and signals on the board, and I do see an increase in high-frequency content compared to the reference trace. Similarly, if the signals are subtracted, i.e. channel 1 minus channel 2, then I see the differential mode noise, which might be coming from DC-DC converters and perhaps of a lower frequency. Although I cannot plot limit lines on the scope directly, it was easy to create a file with the settings and then convert the MXO output into a chart with the lines overlaid. This code is on GitHub and it is quite basic, but it's a start. It would be good to modify the code to configure the MXO4 and prompt the user to follow steps so that everything is repeatable. One annoyance currently is that I've not found a way to export the spectrum from the MXO4 via remote control commands. I've raised this with the manufacturer. If that functionality becomes available, then it will simplify this sort of testing. Anyway, this shows great signs that it is worth improving this test bed, because the ability to quickly test circuits for emissions during development definitely seems feasible with the MXO. For radiated emissions testing, the 500 MHz limit to the MXO license that I've got is definitely a limitation, but as mentioned earlier, it can still provide value to show some of the emissions with harmonics that may have frequency content within the scope bandwidth. I used a homemade probe and decided to use the MXO itself to test the probe. To do that, I had a long trace on a PCB and a block of plastic to hold the probe in a fixed repeatable position. One end was connected to a 50 ohm load. The other end connects to a square wave source so that I could see the harmonics. I used the same fast edge square wave generator that was shown earlier. I can then compare this with the expected output from a square wave to try out different probe iterations. The spectrum also shows that there is no need for a preamplifier, because even with this small probe, the output is easily visible above the noise floor. The dual waveform generator on the MXO is excellent. It's 16-bit and offers 10 volts peak to peak or plus 18 dBm, and sine waves can be generated to 100 MHz and square waves to 30 MHz. Aside from no BNC sync port or a modulating port, I don't see any requirements missing for the typical day-to-day use that people might have for the waveform generator. It is also easier to use than a lot of waveform generators. In the past, I barely used the built-in generators on scopes, but with the MXO, it has become my preference to use this over standalone equipment if I can. For a first test, I had this preamplifier that needed testing. It is an old design from the 1960s, but I recently constructed it to hear what 1960s hi-fi sounded like. I wanted to check the frequency response and that the adjustable controls were doing what they were supposed to do. The general idea is that a frequency tone is generated and fed to the input of the amplifier, and then the amplitude and phase of the output can be compared to the input. There is a frequency response analyzer app license for the MXO, but I was interested to see if I could do it in code to test out the remote control features of the instrument. This sort of analysis requires that the waveform generator output to be also coupled to an input on the scope, so that the amplifier input becomes a reference of both phase and amplitude to compare with the amplifier output. At higher frequencies than audio, then the length of the cable will matter as well. I wrote Python code to access the scope using the PyVisa package. The code is on GitHub and it is easy to use. It will set up the scope and automatically capture the output at different frequencies, and then it will calculate the response and display it. It is easy to edit the code to change parameters such as the desired frequencies. This was a generated chart. The red curve is phase and the blue is gain. This is with the bass control set low, as can be seen from the blue line. Here's the result with the bass increased and the treble backed off a little bit. The y-axis is different on this chart. It is now a flat response to within just over half a dB from 20 Hz upwards. I think the remote control capabilities of the MXO and the documentation for it are very good. It greatly expands what can be done with the scope, since it takes very little effort to fully automate test cases. Here's another test scenario where I wanted to try out an RF mixer. Normally this would need several bits of test equipment, but I wanted to do it all entirely with the MXO. The point of this circuit is that it should perform frequency conversion for radio applications. By using the two waveform generator channels on the MXO, I can provide a local oscillator signal at a high power on the left side and an RF signal at much lower amplitude on the right, and then the output in the middle on port J3 should contain the sum and difference frequencies. I used a small scrap piece of copper-clad board for it. The mixer diodes were BAT54S. They are visible at the lower right. With this setup, with no RF input, I can measure how much of the 6 MHz local oscillator signal was making its way to the mixer output. It was around 44 dB of isolation, i.e. around 1/250,000th of the power of the local oscillator signal. This would be very hard to see or measure in the time domain, but very clear on the MXO spectrum output. Next, I fed a 5 MHz signal into the RF port, and now I could see the sum 6 plus 5 equals 11, and the difference 6 minus 5 equals 1 MHz, clearly visible. What's really neat is that I could also see a decent view of the time domain signal simultaneously, which helps to see how the mixer works. So far, I'd only generated sine waves with the MXO, but I wanted to try the arbitrary waveform generation too. There are built-in waveforms, or you can capture the current displayed waveform from the scope and then replay any part of it. Displayed waveforms can also be exported and modified. The file format is CSV. I wanted to generate a LoRa transmission, and I found the code online to do that using MATLAB. The code creates two I and Q baseband signals, but in my case I wanted to use just one of the waveform channels, so the code was modified to create the LoRa signal at an intermediate frequency, or IF. The plan was that if the LoRa transmission could be generated at the IF, then it could be converted to the actual transmit frequency at, say, 868 or 915 MHz for instance, using an external RF mixer. The MATLAB code is on GitHub. It can be configured to generate any LoRa content, and it outputs a CSV file. There's some header content that is needed, but that's very straightforward to add. Once the file is ready, it is uploaded to the instrument. The file system on the MXO is accessed using a web browser. It is very simple to use. And here's the result. The spectrum view is brilliant. It shows the spread, spectrum nature, and the time domain view can be captured as well. The time domain view shows the frequency being swept, which is what LoRa modulation does. From the spectrum view, the channel bandwidth can be approximately seen, or alternatively, the spectrum view could be downloaded and post-processed. The output looks about right when it is compared with the MATLAB simulation. I decided to spend some time looking at onboard and offboard serial protocols troubleshooting. A neat thing about the MXO is that its entire memory is available for logic capture. In my case, I had the additional memory license installed, which provides a total of 1600 million samples. My main challenge when working with serial protocols is that since protocols can be layered, it is tricky to traverse up and down the stack based on the problem being debugged. For instance, a file read operation might involve dozens of frames or transactions of data, each containing dozens of bytes. A typical use case could be to identify the bottlenecks in software drivers, but just seeing a delay between bytes is not enough unless it can be traced to the software operation that was responsible for those bytes. For this test, I connected SPI flash memory to a Pi-Pico microcontroller and installed the file system. A file read operation took 71 frames with a total of more than 1,200 SPI bytes just to read one line in the file. The view on the scope can be set up to look very similar to the diagram shown earlier, in that the entire operation is shown at the top, and then just below that is a zoomed in view showing the decoded bytes, and then below that are the actual logic signals. This sort of display is very quick to create because of a feature called dual path. What it does is that it automatically ensures that the capture is done with enough granularity for the protocol to be decoded, leaving the user to concentrate on the protocol troubleshooting rather than on the scope setup. The large display allows quite a lot of data bytes to be read directly off the zoom view, and it gracefully adjusts if the amount of zoom is changed. The table is also handy for seeing the protocol decode. What's excellent is the flexibility in exporting that to files. There's several choices including HTML, and it prints a nice summary of each frame and then all of the bytes detail. I would say that the output is about as perfect as it could get. Another option is Python format export, which is super handy for comparing the bytes with a test dataset, or for doing things like performance profiling and to see where bottlenecks are. This chart was created for a file write operation using the Python export feature. The code to generate this chart is on GitHub. Based on this, it is possible to see that the bottleneck for the first part of half of the operation seems to be a packet size limit of 20 bytes, and perhaps even the SPI data rate could be sped up here. For the second half, it looks like polling is going on, so it could be related to the flash memory write operation time. Another thing I was interested in was using the MXO to examine DMX packets, which are used for things like lighting control, but also has other uses in broadcast environments. DMX is tricky to troubleshoot because packets are repeatedly sent and they can be quite large at 512 bytes each. Each packet can be slightly different from the previous one if operations like dimming or colour changing are occurring, and if there's a glitch, you'll want to be able to look through each packet. In other words, you'd want to be quite organised with the capture so that you can check the same bytes in previous packets, for instance, until you can find the issue. For the testbed, I connected up a Pi Pico to an RS485 transceiver and connected that to a 9LED DMX controlled lighting strip. 3 features worked really well together. They were trigger, history and segmented mode. With the trigger set up to reliably detect the starter packets, the MXO starts capturing and labelling each packet with a history value. There's a fast segmentation setting that allows the captures to occur in segments with no data loss, so that every single DMX packet of 512 bytes was captured and stored. For my test, I was expecting 1200 packets, which is just over 600,000 bytes total, and all of that was captured and labelled in the history correctly. The history control allows for switching between packets. It is the same control as that used for analog signals as discussed earlier. All in all, the DMX troubleshooting is actually a delight to do with the MXO. Time to summarise what's good and what's bad. The instrument firmware has been reliable. I've had no software crashes for the 2 months that I've used the instrument. However, with such a new product, there are bugs, although none were showstoppers. Most bugs can be worked around and they have been reported to the manufacturer. A firmware update appeared a couple of weeks ago, so the software is in active development. I hope they come out with more updates at a similar pace until the software is mature. Bugs are to be expected in such a feature-rich new instrument, but it is reassuring that the bugs I've encountered are not what I'd consider severe. Some are irritating though, such as the Python export has certain brackets that are missing, but it is easy to work around by reinserting them with code or a script. Another irritating one is that the default setting is 50 millivolts per division for the probes. It should default to 1 volt or 5 volts per division, I reckon. In terms of functionality that is missing, I'd like to see a remote command available for exporting the spectrum view. With the current firmware, it needs to be saved as a file and then transferred. I think that the math channels should be extended to allow chaining more terms. The instrument seems more than powerful enough to handle it if they would just enable that in the firmware. I also hope that they can enable custom button configuration too. There is a user configurable button, but it doesn't do anything currently. I want to set it to open the acquisition menu, because that seems to be something that deserves a physical button on the scope. I like that productivity is excellent with the MXO. Part of that is down to the user interface because the waveform generator, spectrum analyzer and protocol decoder are all features that are actually easier to use on the MXO than on standalone instruments. Also, none of these features feel tacked on. They are fairly fully featured with extremely high resolution waveform generation and logic capture that can work with the waveform history buffers and huge amount of memory, and spectrum analysis capability that goes a long way to offering features that are not usually seen on traditional swept analyzers. The 12-bit ADC and processing gain at extremely high rates provides a very dynamic insight into signals. Especially subtle behaviour is all visible on that spectrum view, and yet it is still easy to use. So these are some of the reasons why I think it's not unreasonable to suggest that productivity is quite significantly enhanced with the MXO. The screen resolution is the highest I've seen in any scope, and it is used well. I love that the multiple windows can be organised to either fit across the width of the screen or position to the side depending on what is important to the user. Another brilliant feature was the ability to have high quality captures with multiple acquisitions even in the single capture mode. The history and playback functions are to me game changers in how a scope can be used, although they have been present in earlier R&S scopes. There are some additional features which I'm still looking forward to using properly. For instance, there is spectrum gate functionality, which I believe could be used to allow users to do things like investigate the causes of ringing on signals more easily, for instance. There's still a lot of stuff that I need to investigate, and they might make their way into future videos, but for now the review is concluded and I hope you found it interesting. In a long review such as this, it is possible for errors to have occurred, so I apologise if I've made any mistakes along the way. All feedback is welcome. Thanks for watching.